Technology Application Project Curriculum, using Microbit as an example. There will be 6 learning objectives. First, you will learn about Microbit and the coding software, followed by reviewing and analyzing current Microbit projects, learning the basic coding of Microbit, and an introduction to the current Microbit expansion kits. Finally, you will design a project as part of your end-of-term report, which will be peer-reviewed. Now, let's get to know Microbit and its coding software. Introduction of Microbit. Microbit is a pocket-sized computer created by BBC to teach program coding. Through Microbit, students can learn about software coding and electronic hardware at the same time. So, what do we need before we begin? First, you will need a Microbit board, which acts like a little helper acting out the orders from the program. The micro USB cable acts like a butler, transmitting programs into the Microbit. The computer controls all of the coding processes. A complete program is created by stacking programming language and components in a brick-like fashion. You can also write a program using a text-based editor like MicroPython. The QR code on the bottom right corner of the screen leads to additional information, mostly videos. Scan them if you are interested to learn more. Microbit component introduction. This is the Microbit. How many sensors and parts can you identify? On the front side of the Microbit, there are 25 LEDs and 2 buttons A and B on the left and right sides. On the top is the micro USB port that connects to a computer. On the bottom are metal contacts to connect to various expansion parts. On the back is a power port that can connect to a battery box. Next, we'll go through each of the functions. LED light. LED is a small light that is power efficient, small in volume, and simple in design. On the front side of Microbit, there are 25 red LEDs. Each LED can be controlled by a program to turn it on or off. There are also many built-in patterns to choose from. Each individual LED's brightness and darkness levels can be adjusted to create a simple image. What's unique is that these LEDs can also be used as photosensors. Buttons. On the front side of Microbit, there are 2 input buttons, button A and B. You can press either A or B, or both A and B at the same time to produce input values. You can also write programs to tell Microbit what actions to perform when the buttons are pressed. You can even create mini-games by combining button pressing and LED lighting effects. Accelerometer. The accelerometer on Microbit is a motion sensor which measures the acceleration or movement of something. In other words, it senses whether the Microbit is being moved or not. It can sense movements such as tilting or moving in the up, down, left, and right directions, as well as shaking, rocking, front side or back side up. The accelerometer is also frequently used in daily life. For example, when using a mobile phone or tablet, an accelerometer can detect whether the device is horizontal or vertical and switch the screen orientation accordingly. When playing games like racing games, an accelerometer will adjust the movements of the vehicles in the game. When you turn the screen clockwise or counterclockwise, it will tilt the screen. External pins. When you want to use Microbit to control other things, you can use the external pins to output power and control a connected circuit. There are 5 pins on the bottom edge, and they are 0, 1, 2, 3 volt, and G and D respectively. The 0, 1, and 2 pins on the bottom left corner can be used as a signal transmitter or receiver through software control. The 3-volt outputs power at 3 volts, and it is connected to the power supply source such as a battery. The G and D pin on the far right is the ground. Please be aware, do not connect 3 volts and G and D. If you connect 3 volts in G and D, you will burn out the microbit. It's important to remember this. Do not connect the 3 volt and G and D. Temperature sensor. This sensor measures temperature in degrees Celsius. A built-in chip in the microbit is used to sense temperature and returns a response based on the program code, such as displaying the temperature through the LED. For example, we can connect the microbit to a small fan and control it to turn on at a certain temperature. However, the measured value will differ somewhat from the actual temperature, as the reading is not very precise. Digital compass. Microbit has a built-in compass function. The center of the right figure corresponds to the central LED on the front side of the microbit and can detect which direction the microbit is facing. The north is 0 degrees, the east is 90 degrees, the south is 180 degrees, and the west is 270 degrees. The values are adjusted to output the direction of the compass heading. Radio wave transmission. The board uses Bluetooth technology for wireless radio transmission. You can pair up the microbit with a mobile phone or computer through Bluetooth to control its inputs and outputs. Microbit is a device specifically designed to teach software programming. It is a palm-sized computer board with a wide variety of functions. It is easy to use and has many applications. We hope that students can learn about the functions of the software codes by operating the programs. Be creative and use components such as alligator clips, buzzer, or expansion parts to design, and build your unique personal project. Next, we will learn about coding for Microbit. This can be done from 2 online platforms. The first is the MakeCode program editor. It uses a brick drag-and-drop style to operate the microbit, and the effects can be directly presented on the web page. This curriculum will also use the MakeCode programming language as practice examples. You can switch to text-type languages such as JavaScript and Python on the MakeCode page. If the students have basic Scratch knowledge or are at the senior level or higher, they can then use the Python to write text-based codes. The second is the Python program editor. The language used in the editor is MicroPython, which differs slightly from Python and MakeCode. So be aware of the differences when using this language editor. Now that you have learned about the basic microbit functions and programming editors, you can try them out yourselves online. The MakeCode has an all-Chinese operating interface and many tutorials and practice examples to try out from. It is very easy to get your hands on them. There are also many microbit application examples on the internet. Technology Application Project Microbit. The objective of this section is to review and analyze the current Microbit projects. Let's first look at a few Microbit applications. This is a mini game. Can you tell what it's for? Press the A and B buttons to control the red spot on the bottom, which represents the player, and avoid the constantly appearing obstacles from the top. The player who lasts the longest wins. If you get hit, then it's game over. You can also use more than one microbit to interact with each other, such as this application where you can display a heart pattern between two microbit boards by detecting a shaking motion and through a wired connection. Fun, isn't it? Now, think about the functions that we have learned. You will then see that by combining various parts and functions on the microbit, you can create many more fun and exciting projects. However, all good ideas start from copying and observing existing ideas. Please search online for a microbit example video and complete the following analysis. Why did you choose this project? What are its features? What sensors or parts were used in this project? What are the good points of this project? What needs to be improved? We will now leave you to search and analyze the projects. You can do it in groups as well and do a short presentation to share with everyone. Technology Application Project Microbit. The learning objective of this section is to teach basic programming for Microbit. Next, we will learn about the basic functions of the interface and how to operate Microbit. We will start with the LED display, the most intuitive and easy-to-use feature. Controlling LED graphic. What kinds of patterns can you display with 5x5 LEDs? Click on Basic to see various show functions. Show number, show LEDs, show icon, show string, and show arrow north. Now, you may be tempted to drag the show brick to the work area. However, something doesn't feel right. This is because you did not tell Microbit when your commands will be executed or when to execute the show function. These blocks are like dolls without strings. They won't activate by themselves in the work area. To do that, find the block called OnStart in BASIC. Drag it to the editing area on the right, then drag your actions over to it, such as the piece for this indicator light. Now, try to put in multiple show blocks and observe the LED display on the board. You will have about 2 minutes to try out the operations for yourselves. All right, what patterns did you see? You should see a check mark, an arrow, and a heart that appears one after another, then stops at the heart. However, did you feel that the check mark and the arrow flashed by too quickly and weren't displayed long enough? From the Basic tab, find the Pause block and put it after Show LEDs and Show Arrow. Then observe the results. What's different from last time? The pause function pauses the current status. We can adjust the time the icon is displayed by setting the length of the pause time. Next is forever, which is also the concept of looping. This will loop the following actions: show, arrow, east, pause, show icon heart, show LEDs, then continues the show arrow, show heart, show LEDs, etc. The forever piece can work independently and does not need to be put into OnStart. Although the work area is big, You can place the brick commands in any position you like. You should try to avoid clutter by sorting your blocks as neatly as possible and getting rid of any unwanted blocks. Good readability is a good habit to have and applies to coding and text-based editors as well. Now, let's try a little exercise. Please individually create a 5-second or longer animation. light brightness, and display position. Now that we've learned about displaying icons, we can now proceed to adjust the brightness of the LEDs. There are a total of 25 LEDs, 5 by 5. Set the position of the LED by using the plot X and Y. Now, try for yourself and see which LEDs light up, which LEDs are brighter, and which are darker. There are two lit LEDs on the screen. The left one is brighter and the right one is dimmer. Let's compare it to the code. X and Y represent the coordinates of the LED. The top left corner will be 0, 0, not from 1. Starting from 0, if you go right, X becomes X plus 1. If you go down, then Y becomes Y plus 1. For the first LED, the brightness is 255, and the plotting position is X0, Y2. This is the left LED on the screen. For the plotting position, X3, Y1, and brightness of 50, it's the LED on the right. Do you see the difference between the codes for these two LEDs? For the left LED, we used 2 blocks of code to set brightness and position. However, for the right LED, we used code blocks that include the position and LED values together. There are many more pieces that control the LED. Hidden within the More selection, you can combine them as you please. The range of LED brightness is 0 to 255, 0 being the lowest brightness or unlit completely. 255 is the maximum brightness. So, if you want to set one of the LEDs to not light up, then you can choose to 1. Set the brightness to 0. 2. Indicate the positions where the LEDs will not be lit, which will not display them along with the pause block, and you can control the brightness or dimness of the LED, as well as the lengths of time staying lit or dimmed. And that's the fascinating part of programming. There is more than one way to achieve your objective. Let's review again how to plot the position of the LEDs. Starting from the top left corner, 0, 0, the horizontal axis is X and the vertical axis is Y. What position is 1, 2? Did you answer correctly? Now we'll go into the lightning round. What position is 4, 0? 5, 4, 3, 2, 1. Time's up. The answer is at this location. Last question. What position is 2, 3? It's over here. Now that we're familiar with how the LED operates, we can challenge ourselves with more advanced practice. Class assignment. Please observe the way the LEDs are displayed in this video and recreate the same animation effect. Please try to share your observation, including the position of the lights, how it flashes, the brightness, timing, and sequence, and see if you can find a pattern. Think about how you can display this pattern. Let's begin with some simple thought processes, and then we will guide you to do further analysis. we can see that all lit LEDs are in the second circle and are lit clockwise starting from the top left corner. Since this is an infinite loop, we can use the forever block to achieve this goal. Most importantly, the LEDs light up and dim in sequence to the coordinates shown in the video. The LEDs are lit at the same brightness and the length of the intervals is the same. This can be achieved with pause. Use a flowchart to aid in your thinking. Now try it out for yourself. Technology Application Project Microbit. The learning objective of this section is to teach basic programming for Microbit. The concept of variables. The variable is an important concept in programming. It is used in any type of programming language. So, what is a variable? Imagine a variable as a container or space for storage, which is often illustrated as cartons, boxes, or houses. For example, there are two documents on the screen. We can put the lighter colored document A into a paper carton. The carton is our variable, and document A is the value put into the variable. Since a variable is the place for storage, when we want to put in new information, like the blue document B, we can directly put document B into the box, which will replace the original document A. Now that you understand the principle, we can then learn how to use variables and why they are needed. Here is a text example. It could be an email or notification to be sent to someone. The content would be, Document A needs to be sent out today. A copy of Document A is needed in the file database. Please confirm whether or not the seal of approval is stamped on the last page of Document A. At first glance, everything seems fine, but when it comes to handling Document B, all processes are the same. So, how will we handle Document B? First, remove Document A from the first sentence and replace it with Document B. The line then becomes Document B will be sent out today. Do the same for the second sentence, replacing Document A with Document B. A copy of Document B is needed in the file database. Please confirm whether or not the seal of approval is stamped on the last page of Document B. While the three sentences may seem acceptable, what if the code becomes 30 or 300 lines long? Do we have to manually search for them all? This is when setting a variable becomes useful. We set the positions that are constantly modified as variables, which will be represented as a paper carton. We can then place the documents into the cartons based on different needs. When Document A on the right is placed into the left carton variables, the content becomes Document A. To replace it with Document B, change the variable so that the content becomes Document B. Now, think about the song Happy Birthday. When you sing the last verse of the song, Happy Birthday to someone, if the subject is different each time, then the names would be replaced. If we write this song in a program, then the part where the name is can be set as a variable. Now, let's try to operate the variables. Creating a variable. We will need to name the variable. It should be easy to identify. Avoid naming it something like AAA, BBB, XYZ, which can be forgotten after a while, and you will not remember what it represents. Try to carry out the following coding steps. Find the Red Variables tab on the left and select Make a Variable. The screen will prompt you to create a new variable name where you can input the name of the variable. Type in x-coordinate, then press OK. Under the variables, we will see an oval block named x-coordinate, which represents our new variable. There are also two blocks on the bottom, Set x-coordinate and Change x-coordinate, which represent the things we want to put into the variable and how we would like to operate the variable. Now, let's follow the on-screen steps to create a program code and observe the Microbit display on the left. You should see an LED from the top row run across from left to right, correct? Since only 5 LEDs are present in this animation, you can set the brightness and dimness of the LEDs individually. But the purpose of setting a variable is for you to conveniently manipulate the transition of the positions. On start, set the variable of the x-coordinate to 0. Then use the forever block to plot the x-coordinate, and y0. This line means that y will be at the position of 0, but the position of x will depend on the value currently stored in the variable called x-coordinate. Now we pause the code and do the same to set the dimmed LED. Place x into the variable. The change variable is the key to modifying changes. Change x-coordinate to 1. When the code runs to this line, the x-coordinate will change from 0 plus 1 to 1. For pause, 100 milliseconds, the unlit status is paused. It's okay to go with either the red variable or the blue pause first, as their order can be interchangeable. The forever loop will return to the purple plotting block and will light up the LED on the coordinate 1, 0. The code will run like this: 0, 0 lit up, unlit, x-coordinate plus 1, followed by 1, 0 lit up, unlit, x-coordinate plus 1 again, 2, 0 lit up, unlit, x-coordinate plus 1, 3, 0 lit up, unlit, x-coordinate plus 1, 4, 0 lit up, unlit, x-coordinate plus 1, which will then exceed the range of x, so Microbit will no longer display anything. Now that you're familiar with how variables work, it's time to try it out for yourself. Please use variables to control the LED positions and recreate the animation as shown in the video. Here is the answer. We'll now go through this piece of code. When starting up, we set two variables, x and y coordinates, which are both initially set as 0, followed by forever, which plots the positions of the LEDs, variable x coordinate and variable y coordinate. Since both x and y coordinates start from 0, the LED positioned at 0, 0, or at the top left corner will light up. Now, here comes the main event. Variable x coordinate changed by 1, variable y coordinate changed by 1. After these two lines of code, the coordinate has changed from 0, 0 to 1, 1. Followed by pausing 500 milliseconds. Since the position 0, 0 is still lit up, the LED at the 0, 0 position will light up for 500 milliseconds. Finally, the code comes to clear screen, and the LED at 0, 0 position will turn off. Since the code is inside the forever loop block, it will run from the start again, beginning at the purple plot x and y block. The x and y coordinates have become +1. So the position is now 1, 1, and the LED at 1, 1 will light up for 500 milliseconds, followed by the x and y coordinates +1 again, becoming 2, 2. So in the next cycle, the lit LEDs shift downward to the right by 1 grid. You can now see the sequence order of the code, which runs from top to bottom. So the sequence order of this code is plot, change variable, pause, clear screen. If your code is written as plot, pause, change variable, and clear screen, or as plot, pause, clear, change variable, they will all work. However, if you place the change variable before the plot, then the first LED that lights up will be 1, 1. So the logic of the sequence is also important. Next, we will learn about logic and conditionals. Click on Logic, and the three items will appear: Conditionals, Comparison, and Boolean. Under Conditionals, you will see If, Then, Else. You can see that there are blank spaces between the blocks, which will be used to place other codes. If the if condition is met, it will execute the program codes within it. For else, it will then execute the code under the else block. There will be hands-on practice to make you better understand the concepts. The comparisons are symbols like greater than, less than or equal to. For Booleans, they are and, or, not, true, and false. Let's start with the easiest, the conditionals if-else. If it doesn't rain today, then I will go to see a movie. If it's raining today, then I will stay home. Decisions like these happen in everyday life. It's a concept of conditionals. When represented as code, rain will follow if. If rain is true, then it will follow stay at home. If rain is false, then it will follow go see a movie. So the two results, stay at home and go see a movie, will appear in their corresponding groups. Back to the microbit. Here is a demonstration. If button A is pressed, then the number 0 is displayed. Else, the number 1 is displayed. It becomes easier to understand once you read the text aloud. The screen display that corresponds to this code will be the number 1 displayed on the microbit. When button A is pressed, the number 0 will display instead. Here's another code that uses a slightly more complicated conditional. At the start, the variable brightness is set at 0, which applies the concept of setting the variable. Next, inside the forever block, there are green conditionals. If brightness is less than 225, or when the brightness is not at the maximum, then the LED on the coordinate 0, 0 will light up, and the brightness will be the variable of brightness, which is set as 0. Next, the variable brightness is adjusted to +1, so now the brightness becomes 1. Now, think about the relationship between the variable brightness and LED. For now, don't operate the code just yet. Try to think about what kind of display the microbit will output when the code is run. You may have noticed that the variable brightness will start from 0 and gradually increase by +1. So the LED at 0, 0 will gradually increase its brightness from 0 to 225. Compared to the blinking LEDs as shown previously, the gradually lighting of the LED seemed much refined, isn't it? Now, it's time for some practice. Please follow the demonstration and create a breathing LED. Technology Application Project Microbit. In the previous sections, we learned about the basic hardware and software functions of Microbit and tried our hands at controlling the LEDs, the coordinate positions, brightness, and display, as well as learning about the concepts of variables and logics in the Microbit program. We will now introduce the expansion kits of Microbit. First is the buttons. The practice is to move the LED dots left or right by pressing either the left button A or the right button B. We have previously seen how buttons A and B control the LED lights in our project analysis. Like playing a video game, if you press the right button B, the dot moves right. If you press the left button A, the dot moves left. Recall how in our last class we learned to operate the X and Y coordinates? Now we will add conditionals to set our movement. If we press A, then the dot moves left. If B, then the dot moves right. The solution to this problem should now become clear to you. First, let's create variables. Since the LED dot only changes in the X coordinates and the Y coordinates remain unchanged, we will need to control the X coordinates after setting the variable X. Now that the variable is set, configure on start. Observe the position of the LED at the start, which is in the middle of the top row or the coordinate 2, 0. So we will need to set the initial variable value that controls the X coordinate as 2. Next, we will configure the button actions. When the buttons are pressed, the LED at the current position is not lit, unplot. After unplot, variable X or the position of the X coordinate will change to either -1 or +1. Pressing the A button will move left. So the variable is changed to X -1, while Y remains unmoved at 0. Pressing the B button will move to the right. So if the variable is changed to X +1, Y remains unmoved at 0. So, why do we need to set unplot? It's because at start, X is set as 2 and Y is not configured and remained at the default value 0. In this instance, the LED at 2, 0 will light up. When we press the button, we need to unplot the lit LED before we can change the position that the next LED will light up. So, in the button block, the unplot code represents unplotting the X and Y 0. After setting the on button A pressed, unplotting the current LED and moving the X position, we can now set the positions where the lit LED moves to. Use forever to plot the LED of the updated X coordinate. And that's how it's done. When the left button A is pressed, X coordinate -1, the LED 1 grid to the left will light up. Conversely, when the right button B is pressed, X coordinate +1, the LED 1 grid to the right will light up. One thing to be aware of is that intuitively, one may try to light up the LED at the new position, or how to move the positions, and may miss the step to turn off the LED at the original position. It's time for the class exercise. Please observe the video on the right. Please create a program that controls the movement of the LEDs with the A and B buttons, making it so that the LEDs do not disappear during the moving process. You may notice that in our previous operations, when we keep pressing the same direction button, such as button B, the LED will move all the way to the right and disappear outside the border. Now, let's think about how we can avoid this situation. Let's think. To keep the LED within the boundary, we need to determine whether or not the LED position is within the border, which is x equals 0 or x equals 4. Do you notice any keywords? Yes, determine is the key word. We can use logic conditions to help us solve this problem. What will happen if the LED touches the border? If not, what actions will be performed? Think about the border. Is it x equals 0 or x equals 4? For buttons A and B, should we use both or just one OK? You will now have some time to think about the solutions. Buttons. Reference solution to the class exercise. Use conditionals to supplement the unplot and to change the x-coordinate codes as the basis of determination. The actual screen will look like this. Use the green, if then, and package our program codes. This allows the program to determine whether or not the x-coordinate is within the border after the button is pressed, before continuing to implement the unplot and position change. If not, the LED at the original position will be lit repeatedly. Now that we are familiar with inputting commands through button presses, we will next learn how to use sensors. Find where the input is on the menu. Click on Input. The first that appears is the button, which we already know. The next is Gesture, which uses the accelerometer blocks, indicated in the yellow frames. Learn their position so that you can easily use it later. The various sensors on the Microbit can help us create a wide variety of projects. The accelerometer has a total of 7 gesture modes. The screen of Microbit faces up or down, tilt left or right, logo up or down, and shaking. Shaking is a common sensing mode, as the sensor is more readily identified than other gestures. But how does the program know of the Microbit's current status? Please run this code and try to determine the status of the Microbit board when the accelerometer value x, y is at its maximum and minimum. From the operations on screen, we can see that when setting Microbit to display the acceleration value as a number or the icon that appears as scrolling text on screen, the board will display the value detected when we move it. By selecting to display the acceleration value x, the maximum number is 1023 and the minimum number is minus 1023. This is the same for acceleration value y as well. The key points are what actions result in showing the maximum and minimum number. Remember when we were practicing with coordinates? X is the left and right directions, and y is the up and down directions. The same is for acceleration sensing. The x-axis senses left and right. So when you tilt the microbit to the right, the value sensed would be x 1023. Tilt the microbit to the left, and the value sensed would be x minus 1023. The same goes for the y-axis. The maximum 1023 would be when the logo is downward, and the minimum minus 1023 when it is upward. Aside from the x and y-axis, there is also a z-axis. Try it with a connected microbit board and see what kind of changes occur. Now, let's try some examples. Rolling snowball. Try this program and see what happens. Okay, now that everyone has tried hands-on operations, why is the program called Rolling Snowball? When you move the board around, the LEDs in the middle will roll to the tilted side like a snowball. Let's go over the program code. Why do we divide plus 1023 by 510? We have observed previously that the maximum value of x and y is 1023 and the minimum value is minus 1023. So when 1023 plus 1023 and divided by 510, you get about 4.01. When minus 1023 plus 1023 and divided by 510, you get 0. This means that by dividing plus 1023 with 510, the value we calculated will be within 4 and 0, which matches our x and y coordinate values from 0, 0 to 4, 4. The position of the maximum value will be 4, and the position of the minimum value will be 0. We then execute plot xy coordinates, and we will get a program that rolls the LEDs according to tilt angles, much like a rolling snowball. Rolling snowball, border warning. Let's try to improve the code a bit. When the ball rolls to the border, it will display an X, as shown on the screen. This is the code that we have written. We will now add a new function to display an X. We use the green conditionals to control the range of the border. Because the range is between 0 and 4, by setting the x or y coordinate at less than 0.5 or larger than 3.5, an X icon will be displayed. Notice how the OR is used to connect the codes. So, if either one of the 4 conditions is met, an X will be displayed. So, what are these 4 conditions? 1. Variable x less than 0.5. 2. Variable x greater than 3.5. 3. Variable y less than 0.5. 4. Variable y greater than 3.5. If the x and y do not reach the border, the code goes to else. Else, plot the current positions of x and y. However, are we really done just by adding the border conditions? Try to place these codes in your work area and operate the Microbit. Does something seem not right? You will have some time to try it for yourself. See the Microbit status on the left? It looks like the X displayed by the LEDs persists on the screen. So, you may need to add an action like reset or 0 to return the screen to only one snowball. Now, let's go into the details of the actions we just performed. Other than adding the border conditions, we need to change the unplot setting into stop animation and LED enable as true. When the program runs the conditionals and determines whether or not the snowball has rolled to the border, since it is within the forever block, the program will begin again from the stop animation. If there is already an X on the screen, it will be cleared and proceed to plotting the X and Y coordinates. Next, we will go over the new function, wireless transmission by radio. The radio function allows us to use more than one microbit to interact with each other and be more flexible in designing actions. The range of radio set group is from 1 to 255, which means that more than 200 channels are available for use. Setting the same number in 2 or more microbit boards means that they will be in the same channel and can transmit information to each other. For example, if you set the radio group of A, B, and C microbit to 128, both A and B can receive it when microbit C sends a message. This one-to-many feature is a characteristic of radio. You can set the microbit as the receiver or sender of text, numbers, and string values. Let's see how it works in action. For radio component blocks, click on Radio. Please note that it usually needs to work with other components. Now, try out the program code shown on the screen and observe changes to the microbit. Remember to press button A. You can also change the text to be sent and displayed. Through this exercise, we can see that by pressing button A, the microbit on the top will send the text "Hi" through radio to the microbit on the bottom. After receiving the text, the board on the bottom will store the text in the received string and execute the block to show string "Hello." When we try to change "Hi" or "Hello," we see that the "Hi" is sent to the bottom microbit, which senses that a text has been sent. And then execute the block on radio receive, show string "Hello." In this program code, although you can change "Hi" and "Hello" freely, in reality, "Hi" will never display. So, if you want to show both "Hi" and "Hello" on the LED screen, you can achieve so by setting variables like what is shown on screen. When button A is pressed, the sender will display the text being sent, and the receiver will display a response text. Now, let's try to create a mini-game. Please watch the demonstration video. See if you can figure out what functions are used in this mini fighting game and how to create it. Since the game needs 2 microbit, you can guess that it is done through the radio function. Initial setting, set radio group. Then set the variables. Now, how many variables does the game need to use? The answer is 2. One will be set to move the x-coordinate left and right, and the initial value is set at 2, or the middle position. The other variable is the score, which is initially set at 0. Then there's the plotting of the initial coordinate, which is 2, 4. Next, let's set buttons A and B using what we have learned. We create the movement effect using plot and unplot blocks. Since the y-coordinate is at the bottom position, we can set it directly as 4. When button A is pressed, the x-coordinate -1, or move left by 1 grid. When button B is pressed, the x-coordinate +1, or move right by 1 grid. Now comes the main part. Press both A and B buttons to fire bullets. We can see that when pressing both A and B, the dot fires a moving bullet. The x-coordinate will stay at the firing position, but the y-coordinate will move through the grids from 4 to 3, 2, 1, and 0, which visually looks like it is being fired. Then transmit x or the position to the opposite microbit, and the bullet will come from the same x-coordinate. Now that we have configured the firing part, we will now set the receiver of the bullet. We need to receive the position of the bullet and keep it moving. So we will use the for, do block to plot the received x-coordinate and the y-coordinate that moves. If the bullet touches the opponent's position, a text signal is sent back and a score of 1 is shown. The scoring will be shown for 0.5 seconds, then reset, and the game continues. Remember that when the bullet hits, the return signal cannot transmit a number, or the opponent's microbit will read it as a bullet that is fired. How do we set the scores? When receiving the signal that the opponent is hit, your own score will increase by 1 and display on the screen. After 0.5 seconds, the display resets and the game resumes. Use stop animation to clear the score, replot the LEDs, and return to the shooting screen. Wireless transmission, radio class exercise. Now, try to create an advanced fighting game where one wins after getting a score of 5, and the winner's side displays W and the loser's side displays L. Let's introduce another new function, digital compass. Microbit has a digital compass function. Before using, it needs to be calibrated first. You can find this function in the More section under Input. Note that when calibrating, do not place any metal objects nearby, or the sensed value may be incorrect. Heading. After the compass is calibrated, you can use the compass heading to set the functions. As shown here, using the forever block, and store the compass heading in the heading variable. We can then use conditionals to complete the task, which is a bit more complicated here. We start with if, followed by else if, the second else if, and a third else if. We then end with else, a total of 5 blocks. As a reminder, the structure looks like start with if and end with else, and you can place many else-if blocks in between, depending on the needs of your program. The conditionals are controlled by the number in the heading. As previously mentioned, the east, south, west, and north headings, starting from the north, will be 0, the east is 90, the south is 180, and the west is 270, which completes 360 degrees full circle. The first condition is set as if the heading is less than 45, then show arrow north. By doing so, if the heading is not less than 45 or greater than or equal to 45, the code goes to the next else if conditional. Next, we will determine whether or not the heading is less than 135. If it's less than 135, then show arrow east is displayed. Next, if we determine that the heading variable is less than 225, then we display show arrow south. And the last else if, which shows the west, follows the same concept. Now, think about this. Can we set the first if as if heading is less than 135, followed by else if heading less than 225, and else if heading less than 135? You will see that we can't actually do it. Suppose the detected heading is 123, which would be near east. But if we set the conditionals like our hypothesis, when it runs from the top to the bottom, the heading 123 will directly meet the requirement less than 315, which will show the arrow toward north. Therefore, it's important that we determine the order of the conditionals. In fact, the program code will make the microbit display an arrow to the right and show the number 90 degrees on the top toward the east. And so, this is the digital compass that we have just made. After going through so much trouble to write the codes for a digital compass, does this mean that we have to rearrange all these bricks when we want to use them again? This is when function becomes useful. The principle of function is to package the program codes or commands into one function, which we can directly access the next time when we want to use it. You can find function under Advanced tab. The complete function will look like this. Now, let's learn how to create functions step by step. First, let's create a name of function, which we will call function here for simplicity. If needed, you can add other parameters for the function use. After clicking on Done, you will see a new function block in the work area, just like setting a variable block. You can now drag the function block and start using it in the work area. Now that we've learned about setting function, let's try another exercise. Please package the digital compass program into a function and set to receive the parameter of heading. We'll pause the screen to let you think about it and try it out yourself. If you want to configure more ways to use the device, you can go to Input and try out other sensors. Aside from the buttons, acceleration, and heading, you can also find a sensor for light level and temperature. With these, you can create programs that tell the Microbit to respond to the different levels of brightness and temperature. Try these functions out for yourself. Please design a program that makes Microbit detect comfort level. 1. Define light level greater than 170 and temperature between 25 and 30 degrees as comfortable and show a smiley face. 2. Define light level greater than 100 and temperature between 15 and 40 degrees as moderate and show a bored face. 3. For light level and temperature outside the above ranges, define as uncomfortable and show a sad face. Here is an example using the emulator. You can adjust the temperature and light levels to make the LEDs display different faces. Now it's time for you to try it out for yourself. Technology Application Project Microbit. We have learned about the functions of the microbit. Now we will conceive and design projects. Before creating your own project, let's do an exercise and review how to combine various functions of the microbit. The QR code on the bottom right leads to a web version of this game. We are trying to recreate Flappy Bird. You will have some time to try out the game for yourself. When you are playing the game, try to observe the following. The elements shown on the gameplay screen, like the bird and obstacles, how they are controlled and moved, how the bird flies, and how scoring is calculated, and how the game ends. Now, try out the game for yourself. The first step of game design, create a Sprite character. Use Microbit's game block to recreate your Flappy Bird character. Go to the Advanced menu and select Game. You will see many blocks related to game creating. The first step is to create a sprite and set the starting position of the sprite. Set the sprite variable and create a sprite somewhere. Because we are using a simple version of the game in Microbit to allow your Flappy Bird to be easily identified from the pipe obstacles, we will make the Flappy Bird sprite blink. Use the blocks on the screen and select the pull-down menu to blink. And place this block after the created sprite. Now we will set the flying rules. In the original version of the game, the bird will fly up and down when you tap the screen and then fall down. The bird will fly up again when you tap the screen again. By doing this, you control the bird to maintain the height you want to avoid the coming obstacles. For the Microbit version, the tapping is configured as pressing A or B buttons to make the bird fly up. To fall after flying up, we will achieve the effect by programming the codes so that the sprite moves up 3 grids, then falls down. The bird will fly again until the player presses either A or B, which will again fly up 3 grids and then fall down. Try it out for yourself. How would you arrange the codes to achieve the same effect as shown in the video? Here is a reference solution. Use the conditional if, else to set the status corresponding to the button pressing. If any button is pressed, then repeat the execution 3 times. Make the y-coordinate of the bird sprite -1 or move up 3 grids as -1, -1, -1, else the sprite is y-coordinate +1. If you feel the sprite is moving up and down too fast, you can adjust the milliseconds of the pause to make it move slower. A game should have a beginning. Having it start when power on isn't too refined. Set it so the bird can only be controlled once buttons A and B are pressed together. Notice the details in the video. The bird sprite is already displayed when the board is powered on. So, how should we configure it? First, we need to set a condition for game start and set it to run the condition when both buttons A and B are pressed. Here, we'll demonstrate using the variable start to control the start of the game. At the start, the variable start is 0. When A and B are pressed, execute the action change variable start to 1. Then use another conditional to envelop the game section. This conditional will be if start equals 1. If equals 1 is true, then the game will start. And execute the parts where pressing buttons A or B moves the bird up and down. If equals 1 is false, then the game has not started yet and no actions will be carried out, remaining at the start up status. This means that the variable start equals 1 condition signals the microbit whether to start the game or not. You can also try to change this message into something else. The concept being, if it meets the requirement, then the game is executed. If it doesn't meet the requirement, then maintains the Sprite startup status. Now try to operate the process. You can also try to adjust settings or parameters, such as set button A as game start, B as control, and no reaction when both A and B are pressed. The key point is to be familiar with the game structure and concepts so that you know how to use the functions when creating your own project. After setting the start of the game in Sprite Control, we will now place some obstacles in the game. Obstacle creation. Try to create an array variable, which will save all obstacles. Next, set the second variable obstacles whole y to store the y position of the random obstacle opening. The size of the opening is set as 2 LEDs. The obstacle sprite is created and added to the obstacle array. After setting, try to refresh the program and see if the obstacle opening changes position. After creating obstacles, we will now move them. Through changing the x-coordinate of obstacles and setting the intervals of obstacle movement, we make all sprites in the obstacles array to move one grid left together every 1 second. Now that the obstacles are moving, we will now need to clear the obstacles when they move to the border. When the first element of the obstacles touches the left border, this means that all obstacles have reached the border. If there are still sprites in the obstacles array, or whether or not the length of the obstacle is greater than 0. If it's greater than 0, then the sprite is removed. Let's pause for a bit and examine the board. We should have set the Start Game button, Flying Bird, Moving and Disappearing Obstacles. You can adjust the speed at which the obstacles move and the starting position of the bird, which in turn adjusts the difficulty of the game. If your game ends up different from the function shown in the video, you can compare it with the program code shown on the screen and see what went wrong. Automatic obstacle generation. Over time, the game automatically generates an obstacle. You can decide the time at which obstacles appear and do not have to follow the demonstration. Try to write the program to achieve the effect shown in the video. Game over. This is the last step of your game. When the bird that you are controlling touches the obstacle, the game is over. For your reference, this is the program code for Flappy Bird. Here we set the variable time that controls the time and clean up our codes. In the forever loop, and add the condition for ending the game. This code is a bit more complicated. You can compare it to your code and see what is different and make adjustments as necessary. Bonus topic. Here are some configurations that can improve your game. Try to incorporate these effects. You can receive extra points or rewards if you can complete these functions. 1. Add sound effects to the game. For example, flapping wings, game start, and game over side effects. 2. Scoring function. 3. Increase the speed as the game progresses, or use your creativity to make something completely unique. The lower right is the complete program code of Flappy Bird, excluding the bonus topics for your reference. The following is the explanation on microbit sensors and links to the related program code examples, project materials for students, and official website and resources for students to use. References for the Microbit official website, sensors, and related program codes. The following are explanations on microbit expansion kits currently available in the school and links to the related program code examples. If your school has purchased microbit expansion kits, you can prepare the website resources of various kits beforehand and let the students research on their own. If you only purchase one of each kit, let the student teams choose a kit that they may use so they don't overlap between teams. Make them available for students to use and test during the project period. You can even consider allowing students to bring the kits home for testing. Technology Application Project Microbit. Finally, we are now at the section on final project report and peer evaluation. Please conceive a project and present it in video form at the designated time. There will be two parts in this section. One is team brainstorming. Each team has to produce a design draft of their project and discuss it with their teacher first. After making sure that everything is fine, then begin the creation process. The second part is the work schedule planning. Each team has to plan out the work progress chart. Here is an example of the progress chart for your reference. After confirming the progress chart, in order for the students to finish their products and produce a showcase video on presentations day, have the students devise the work progress chart and report their progress regularly. We suggest sharing the progress chart with instructors to get an idea of each team's progress. Final presentation. Please go to the shared drive and view the presentation video of each team. Score and give encouragement to the other team's video, and don't evaluate your own team. Creativity, practicality, aesthetic design, and overall scoring. Areas that are great or need improvement. After receiving the score and feedback from each team, you could sort them and give feedback to the teams. Let them know the strengths and weaknesses of their own projects and how they can improve in the future. Thank you for listening.